We spent the last lecture talking about dielectric displacement, and we saw that for no lead wires, meaning no external power source or applied electric field, D is 0, so it's constant. And I want you to contrast with the case there is a power source. E. In this case, I'll show you the first case where E is constant. How do you get what's the simplest case where the electric field across the material is constant? Well, you have E equals 0. And the best way to do that, the easiest way to do that is to make it short circuit. So we have a material, electrodes on top, electrodes on bottom, have some polarization like that, and we simply connect the top and bottom. So no matter how much we pull on it, you know what happens when you pull on it like this. I told you, right? Negative charges here, positive charges here. This goes up, this goes down. Positives developed here, negatives developed here. But wait, we connected these potentials with this wire here. So basically the positive charges is going to flow down. The negative charges is going to flow around. And they're going to meet, basically. So we're not going to have any stored energy. No stored electrical energy. Why? Because its charges are just leaving. Unlike the case where we have here, we are just pulling on it again. And we're getting positive charge here and a negative charge here, but we have stored energy. We have an electric field. Check. We have an electric field, so there is stored energy here. So, but in this case, right, in this case, we have this conclusion. No stored energy. No electrically stored energy. So what exactly is happening? Do we have any stored energy? Yes, we do. We have no electrical stored energy, but we have mechanical stored energy. Again, this equation is going to hold. It's not going to be infinitely stiff. I mean, it's not going to be infinitely compliant. We'll have a compliance, but we'll call this compliance SE. Right? This compliance is known as SE. And what's the other compliance? SD. Basically the response in terms of strain from a stress. So in this case, we'll have just a regular force on it, but no leads. I'll just draw like that. There's no leads on this one. And this is SD. So which one do you think is tougher? In this one, we're only storing mechanical energy. In this, we're storing electrical energy and mechanical energy. But both of these terms are hidden inside of this, because when you're pulling on it, you're feeling the pulling, but the pulling is both creating electrical energy and mechanical energy. So you're doing two things at once, but you don't really know what you're doing. You kind of it feels like you're pulling really hard, even though two types of energies are being stored. So which is higher? Now you may get this answer wrong. SE is higher. But I think I tricked you a little bit. The Young's modulus of YD, constant displacement, is higher. See, this is constant electric displacement, which refers to this case. And this is constant electric field, which refers to this case. So in this case, YE is higher and YD. So we have to really understand what is going on. One's upside down, right? Because we're compliant is more, something that's more compliant is less stiff. So here we have double energy, and here we have a single energy. And depending on how much they are coupled together, depending on that, we get different values for these. So we'll kind of be discussing that next time when we talk about the electromechanical coupling factor, which we're not able to discuss because we covered boundary conditions. And what are the two boundary conditions? Constant electric field, 1, and constant dielectric displacement, 2, which I discussed in the opposite order. Now let me give you this case. Let's say I set the electric field to a number. Let's say 5, I don't know. But, corresponding to some voltage. So I have a material. I apply delta V across the material. Say this is the positive side, let's say this is the negative side. So we have this, and therefore, what's going to happen? We're going to generate positive charges here, or negative charges on the bottom. And therefore, we're going to get an electric field going that way, which will make the material shrink a little bit because we're applying electric field opposite to the material. And again, just to kind of think about it, we have a plus here and a minus here. Minus wants to go to that side, plus wants to go to this side. So we're kind of squeezing the material. And thus the material is getting smaller. But in this case, what happens? Okay, let's say I'll let everything go into equilibrium. We've established, the new surface over here, and the material got a little smaller over here. So the material got shrunk. The material shrunk basically. And also remember, when a material shrinks, it also expands on the other way. But that's another topic that we'll go over later. So we have this electric field across the material, and let me tell you, what if I pulled on it at this point? I applied an electric field, and then I pulled on it. We still have constant electric field. Okay? We have constant electric field. The reason we have still constant electric field, the reason we'll still use this term to describe the stiffness in this case, is because all of these charges, when you pull on it, extra charges are generated, right? Let's say we pulled on it. What kind of charges start generating? This positive goes here, so we develop more positive charge. This negative goes here, we develop more negative charge due to this pulling. But what happens here, this is a charge imbalance, and we are forcing the material to undergo a certain electric field. We are forcing it to be an electric field, and electric field is directly related to how many charges are on the surface. So when you are generating more charges, the voltage source is going to absorb those charges, those extra charges which you are generating, and it's going to maintain the electric field at the voltage specified. So even though we pull on it, while we have an applied electric field, the electric field is still constant because of the power source. In the same case, we'll also go with alternating electric field. If we have an electric field which is like equal to a sine function, we'll still be using this electric field because the charges on the surface are still controlled externally. And when they're controlled externally, we're not allowing any stress to screw things up. We're not allowing any stress to add extra charges because this will just be taken out by the power source as a current. Thank you for watching. Next time we'll be covering the electromechanical coupling factor, finally, which is known as K squared.